Imagine flipping a coin that remains suspended in mid-air, simultaneously showing both heads and tail until you catch it and force it to choose one outcome. This captures something profound about quantum reality. Particles exist in multiple states at once until observed. Yet, in our daily experience, time marches relentlessly forward. Coins land, clocks tick, and the past feels permanently fixed. This stark contrast between quantum strangeness and our macroscopic experience of irreversible time lies at the heart of physics' deepest puzzles. How does the arrow of time emerge from seemingly timeless quantum laws? The Shrevinger Equation, which governs quantum evolution, is perfectly reversible. It works equally well whether time flows forward or backward. Unlike classical physics, where friction creates obvious temporal direction, quantum mechanics at its most fundamental level shows no preference for past or future. This creates a profound puzzle. If the microscopic laws governing reality are time-symmetric, how does the macroscopic world develop such a clear temporal direction? Classical physics assumes objects possess definite properties independent of observation. Quantum mechanics shatters this assumption. A quantum system exists in superposition until measured, then collapses into a definite outcome. The act of observation doesn't merely reveal reality, it helps shape it. Consider the double-slit experiment. An unobserved electron behaves like a wave, creating interference patterns. But when we observe which slit it passes through, it acts like a particle. Its path, whether it traveled as wave or particle, isn't determined until measurement. This suggests that in coherent quantum systems, the past is not a single trajectory, but a set of possibilities that crystallize into definite history only upon interaction. The tension between time-symmetric quantum laws and irreversible macroscopic time is resolved through decoherence. When quantum systems interact with their environment, measuring devices, air molecules, stray photons, they become entangled with that environment. This process causes systems to evolve into classical outcomes, even though the overall evolution remains reversible in principle. What makes decoherence effectively irreversible is the irreversible dispersal of quantum information into the environment. Once information about the original quantum state spreads into countless environmental degrees of freedom, it becomes practically impossible to retrieve and reverse the process. This irreversible loss of quantum coherence gives rise to time's forward flow. The second law of thermodynamics states that entropy tends to increase over time, providing temporal direction. On a microscopic level, this entropy increase results from decoherence. As quantum systems interact with surroundings, they evolve from pure low entropy state to mixed higher entropy state. So, the quantum to classical transition creates the thermodynamic arrow of time. So, the quantum to classical transition creates the thermodynamic arrow of time. In Wheeler's delayed choice experiments, a photon passes through a double slit before any measurement is chosen. Yet, the later decision of how to measure it seems to retroactively determine whether the photon behaved as a wave or a particle. Cosmic scale versions of these experiments suggest that decisions made now can correlate with the behavior of ancient photons. However, the idea that these measurements determine the past is debated. In interpretations like Copenhagen, the focus is on correlations between the measurement and the system's state, not a literal alteration of past events. The system must remain coherent until measurement for these effects to occur, and the apparent retrocausal influence reflects the quantum system's indeterminate history, which only becomes definite upon observation. This remains a matter of interpretation, with no consensus on whether the past is truly reshaped. The unresolved tension between quantum mechanics and general relativity deepens questions about time's fundamental nature. In Einstein's theory, time is dynamic and intertwined with space. In quantum mechanics, time is treated as a fixed parameter. Efforts to unify these frameworks suggest time may not be fundamental at all. Carlo Rovelli's relational quantum mechanics proposes that time arises only through interactions between quantum systems. Other theories, like the holographic principle, imply time itself may be a projection of deeper, timeless laws. What we perceive as time's passage could be a shadow cast by more fundamental, timeless reality. The evidence from quantum mechanics reveals a remarkable truth. Time's arrow is not built into the universe's fundamental structure, but emerges from the quantum world's interaction with its environment. While the underlying quantum laws are time-symmetric, our everyday experience of time's forward flow comes from a different source. When quantum systems interact with their environment, their information becomes entangled and spreads out everywhere. This process, called decoherence, is theoretically reversible but would require tracking and controlling countless particles simultaneously, practically impossible. This irreversible spreading of quantum information creates what we experience as time's forward flow. The universe does effectively remember the past, but only because reversing all those quantum interactions would be practically impossible. Time's arrow emerges from this inability to turn back the quantum clock. Thanks for watching. If you found this video helpful, give it a thumbs up and don't forget to subscribe to the channel.